right, hello everybody. We are picking up from where we left off in class yesterday with lesson 1B.2 on holes and vertical asymptotes from our analytic form of a function. And so we are going to pick up with this practice problem real quick. And so with practice problems, I would like you to pause the video, try them, come up with an answer, and then start the video again so that you can see what the solution should be. So here in the xy plane, the graph of a rational function g has a hole at x equals 6. We want to know which of the following could be an expression for g of x. All right, pausing here would be good. Okay, so if you're back now, what we're looking for is understanding that the factor that we need to get a hole at x equals 6 would be x minus 6, because x minus 6, if we set that equal to 0, adding 6 to both sides would give us that x value of 6. So we're looking for where we have the same multiplicity in the numerator and denominator for the factor of x minus 6, or where the numerator is a greater multiplicity. And we find that here in choice B. They're equal multiplicities. So choice B is our correct answer. All right. Next practice problem, you've got a function b, which is given as this rational function. In the xy plane, which of the following is true about holes in the graph of b? So pausing here would be good. All right, so here we're looking at understanding that we would need to complete the factoring of this trinomial to be able to really figure out what's going on with holes and vertical asymptotes and whatnot. So here we've got x minus 3 times x plus 2. So our factor of x minus 3 in the numerator and denominator, they have equal degrees. So we're going to get a hole from there. And setting x minus 3 equal to 0, we'd add 3 to both sides. So that's going to give us an x value of 3. For the x plus 2 common factor, the degree is greater than denominator. So here for this one, we get a vertical asymptote. All right, so let's see what our answer choices are. So there are holes at both x equals negative 2 and x equals 3. Not true, because the x equals negative 2 is a vertical asymptote, so A is out. There are holes at both of them again. Not true. Here in choice C, it says there's a hole at x equals 3, and D also has a hole at x equals 3 only too. So now we have to look at the reasoning for choices C and D. It says because the multiplicity of negative 2 in the denominator is greater than the multiplicity of negative 2 in the numerator, and because the multiplicity of 3 in the numerator is equal to the multiplicity of 3 in the denominator. Here it's saying the multiplicity of negative 2 in the denominator is equal to the multiplicity in the numerator, and multiplicity for 3 in the numerator is equal. So here it's talking about they're both equal. Here they're not both equal. And this one gives us the right reasoning because the denominator multiplicity is greater for negative 2, and for the 3 the multiplicity is equal. All right, now we're going to look at an example. And for this example, it says the rational function n is defined by n of x. In the xy plane, the graph of n has a hole at the point with coordinates c, l, and it wants us to find the values of c and l. So c and l, we need to realize, represent our x and our y coordinates for the hole. So this is a hole, and so we're looking for both x and y, but we need to make sure we use the variables that they've been assigned, which are c and l, okay? So here, we first are going to need to do some factoring to figure out where we have that hole, what the x value is, which is called c here. So with the numerator, we have to see a GCF of x, and so that's going to give us x times x squared minus 4. And then we have to see the x squared minus 4 is a difference of 2 squares, so that is going to give us x times x plus 2 and x minus 2. And in our denominator, we have a trinomial that has a GCF of 1, so we just have to factor into binomials, which would be x plus 2 and x plus 1. So here we can see that we have equal multiplicities for the factor of x plus 2, so that's going to give us a hole. And when we set x plus 2 equal to 0, subtracting from both sides gives us x equals negative 2. But because of the way this is worded, the x is our c. So we want to say that c equals -2. All right. So now we want to know, how do we figure out that y coordinate, which is called L in this problem? What we have to do is reduce the factor that gave us the whole. So x plus 2 and x plus 2, those would reduce to 1. And so we call this the simplified function. Becomes just the x times the x minus 2 over an x plus 1. So this, remember, is our n of x, and n of x is our function notation, so that's our y. So we have to understand that when we plug in our x value of -2 here, what that's going to give us is the y coordinate of that point or whole. So this would become -2 times -2 minus 2 over -2 plus 1. And then we just have to be careful to do the math correctly here. So here we are looking at -2 plus -2, here would be -4. -2 times -4 would be +8. -2 plus 1 is -1, and 8 divided by -1 would be -8. So that's our y coordinate. But again, in this problem, y is designated as being L. So we want to say L, capital L, equals -8. And that gives us then both parts that they're asking for. All right. So now let's take a look at this one. So we need to go back to the concept portion. We haven't talked about limit notation yet with holes, and that is what this particular example is about. So going back to our concept portion here, holes and limits. So the idea of writing the behavior of the function as it approaches the hole is, so here we're using the c and the L again. So our L is our y coordinate, and so we would be equal to, in our limit notation, we would be equal to our L value, or our output, our y. So that is the y coordinate of the hole. The x coordinate of the hole is found here with the c. And you might notice, or hopefully you notice, there's a little superscript after the c. For the left, it's a -1, and for the right, -1, it's not a -1, it's a negative sign, and for the right, it's a little plus sign. And so that means, so this would be our x coordinate of our hole, which in this definition is called c. And the superscript of a negative sign or a positive sign tells us which side we're approaching the hole from. So let's say we had like a curve that went like this, and we have this hole, say right here, okay? In fact, let me draw that a little more appropriately without a line through it. So we've got our curve, we've got a hole, and then the curve keeps going, okay? So we would use the limit notation over here on the left, that x is going to our c value, or x coordinate, from the left, because we're heading towards the hole from the left side. And on this one, this is when we would use our c, our x is going towards c from the right, and we do a little plus sign. So x is going towards c from the right, and that's when we would use that one. So whether it's a minus or a plus depends if we're on the left or the right of the hole and heading towards the hole. And then we use our function notation here. Here it's called r of x, but whatever it's called, that's what we use. So let's go back to that example now. So here we have a rational function f, and it says the graph has a hole at x equals 1, which we can see. There's our x equals 1 for that hole. And so we want to know which of the following is true about the graph of the function as values of x become sufficiently close to 1. So this is the idea of, we've got this curve, we've got this hole, and the coordinates of that hole are 1 comma something. We don't know that yet. And we want to know which we're looking at. So we can notice they're all pluses on the superscript, plus, plus. So we're not talking about left or right. We're just talking about getting close to 1. So we know this is supposed to be our x value. So these guys are out because -2 is not our x value. And so we're looking at either A or B because it has the right limit portion. Okay. So now we need to know what is the y coordinate of our hole. So again, what we would do is we would reduce our common factor here to 1, and then we would look at the simplified function, which is just x plus 7 over x minus 5. And we would plug in the x coordinate of our whole number. And so that would become 1 plus 7 over 1 minus 5, which would be 8 divided by -4, which is -2. And so that has to be what we're equal to. And that would make B then our correct answer. All right, let's take a look at, looks like a similar problem here as a practice problem. So again, I recommend you pause the video, give this one a try, and then start it again when you're ready to check your answer. All right, so welcome back. We're looking at which of the following is true about the graph of the function as values of x become sufficiently close to -6, because there's a hole at x equals -6. So we know that this portion should be a -6. And so we've got -6. This does not have -6. This does not have -6. So again, we're down to A and B. And now we want to know what is the y coordinate of the hole. So we would reduce out our common factor of x plus 6 that gave us the hole. That becomes 1. And so now we have that our p of x in its simplified form would be 2x over x plus 3. And so now we're going to plug in our x value from our hole, -6, and that would give us 2 times -6 over -6 plus 3. And here we get -12 divided by -3, which would be a positive 4. And so that gives us a choice B. That 4 matches that right there. All right, let's take a look. We've got another practice problem here. It says, which of the following could define r of x? So again, pause the video, read through this, start it again when you're ready to check your answer. All right, welcome back. So let's see what we got here. So we have a hole at x equals 3. So we need to know that that is going to come from a factor of x minus 3, because when x minus 3 is set equal to 0, we'd add, and that would give us our x equals 3. And we need our factor to have either equal multiplicities in numerator and denominator or larger in the numerator. So looks like we are dealing with this one right here. And, or this one is also a potential, because it's got the x minus 3 in both. This does not have the correct factor, so it can't be A. And D does not have the correct factor, so it can't be D. So we're down to B and C. So this is the second part of the problem. So it says input values of r sufficiently close to 3, so that's our x equals 3, correspond to output values arbitrarily close to 8. This is describing our y value. So this is saying we have a hole at 3, 8. So we need to know, does B or C, in its simplified form, give us that output of 8? So here, if we reduce out the x minus 3's, we get 8 times x minus 2 over x plus 2. Here, if we reduce the x minus 3's, we get x plus 5 over x minus 2. So we have to, again, plug in the 3 for the x's and do the math to see which one gives us an 8 as an output. And so this would be 8 times 3 minus 2 divided by 3 plus 2. This would be 8 times 1, and that would be 8 divided by 5. This one would give us 3 plus 5, divided by 3 minus 2, which would be 8 divided by 1. So which one of these is equal to 8? This one right here. So C would be our correct answer. All right, so now let's take a look at these next examples. So now we're looking at finding the x-coordinate of any vertical asymptotes. So earlier we did problems where we focused on finding x-coordinate of holes. Now we're focusing on vertical asymptotes. So we have to remember that for vertical asymptotes, that what we need is the degree in the denominator is greater, or we have a unique factor in the denominator. Those are the two situations that give us that vertical asymptote. So again, we first want to look to see, do we have any, what do you call it, anything else that we have to factor? So here in this first example, we have this, that has a GCF we have to factor out, and this trinomial that we have to factor. So that's going to give us x times x minus 3, and this is going to give us x minus 4 times x plus 1. So we are looking for factors where, and I'll rewrite this for clarity here. So we have x minus 4 to the third power times x plus 1. In our denominator, we have an x minus 3, an x minus 4, and an x plus 1. Okay. So your x minus 4s, your numerator is greater. So this is going to give you a whole. Your x plus 1, your degrees or multiplicities are the same. So this is also a whole. So we are going to get vertical asymptotes from these two unique factors. So each of these is unique. So we get x equals 0. And when we have x minus 3 set equal to 0, undoing the subtraction with addition gives us x equals 3. So we have vertical asymptotes at both x equals 0 and x equals positive 3. All right, second example. So in the second example, there isn't anything that we have to factor. Everything is a nice prime binomial. So now we're just going to compare and look at our multiplicities. Let's use that. So our x plus 6, our degree in the denominator is larger. So that's going to be a vertical asymptote. Our x minus 5s, the degrees are the same. So that's going to be a whole. And the x plus 2 is a unique factor. So that is also going to be a vertical asymptote. So we have our x plus 6 equals 0. Subtracting would give us x equals negative 6. Our x plus 2 equals 0. Subtracting would give us x equals negative 2. So we have vertical asymptotes at both x equals negative 6 and x equals negative 2. All right, so let's try a practice problem here, where again we're looking for those x coordinates of our vertical asymptotes. So pause the video, do both of these problems, and only restart the video once you're ready to check your answer to both, because I'll do them both one after the other. All right, welcome back. Let's take a look. So in this first one, we have to factor this trinomial, which would give us an x minus 7 times an x plus 2. So when I look at this, my numerator is x times x minus 7 times x plus 2 quantity squared. And in my denominator, I have x to the third. These two x minus 7s combine to become x minus 7 squared, and then I've got x plus 2. All right. So our factor of x, our denominator's multiplicity is 3, which is larger, so this is going to give us a vertical asymptote. The x minus 7, the denominator's multiplicity is 2, which is larger. That's going to give us a vertical asymptote. And our x plus 2 factor, our numerator is larger, so this is going to give us a whole. So we're just going to deal with the first two factors. So the first factor is x, and that just becomes x equals 0. The second factor of x minus 7, we would undo the subtraction with addition, and so we get x equals 7. So we have vertical asymptotes at both x equals 0 and x equals 7. With the second one, there's no factoring that needs to be done, so we can compare. With our x minus 8 factor, the multiplicity is larger in the numerator, so that's a whole. Our x plus 1 is a unique factor in the denominator, so that's going to give us a vertical asymptote. And our x plus 3, the multiplicities are the same, so this is also a whole. So we're only going to get a vertical asymptote from the factor of x plus 1. And if we set x plus 1 equal to 0, we subtract, and that gives us x equals negative 1. So we have a vertical asymptote at x equals negative 1. All right, let's take a look at this practice problem. So in the xy plane, the graph of the rational function g is a vertical asymptote at 6, or x equals 6. Which of the following could be an expression for g of x? All right, pause the video, make your decision, start it up when you're ready to check. All right, welcome back. Let's take a look. So since this is a vertical asymptote, I need to know my factor, which would be x minus 6, because if I set x minus 6 equal to 0, that's what gives me, x equals 6. So here I have to know that I'm looking for x minus 6 in both, either as a unique factor in my denominator, or when my denominator's multiplicity is larger. So here I have a unique factor in the numerator, so that is not going to give me vertical asymptote. Here my multiplicities are the same, so that's a whole, not what I'm looking for here. Here I have a unique factor in the denominator, and so that is where I'm going to get my vertical asymptote. So choice C is correct. All right, let's look at this one. So here the function f and the function g, consider the rational function p, which is g over f. Which of the following is true about the graph of p in the xy plane? So pause, make a decision, and then restart when you're ready to check. All right, so welcome back. Let's take a look at it. So if we take a look at what we've got here, so we have f is on the bottom, so our p of x, the f part's in the bottom, so that would be x plus 2 quantity squared. Our g is in the top, so we have x plus 2 and 3x minus 2. Okay, so now we're looking at, wholes and vertical asymptotes. So we have to look at our matching factor here of x plus 2, and our degree is larger in our denominator, so we're going to get a vertical asymptote. And the 3x minus 2 is in the numerator. We haven't talked about this yet, but that's actually going to give us a 0. It does not give us a whole or a vertical asymptote, so we just ignore that. So here it says the graph of p has holes at -2 and 2/3. Nope. Here it has a hole at -2 and a vertical asymptote at 2/3. Nope. Here it has a vertical asymptote at -2. That's true, because if x plus 2 equals 0, subtracting gives us an x value of -2. But we just talked about how the 3x minus 2 is actually going to give us a 0, so it does not give us a hole. Then the graph of p has no holes and a vertical asymptote at x equals -2. That's actually true. There are no holes. There's just the vertical asymptote at x equals -2. All right, that's all of the problems in this lesson. You can rewatch, of course, as much as you like, and when you're ready, work on the assignment. Have a great day. Bye.